This is part 2 of the Oneway ANOVA, looking at the relationship between noise and memory. In the last video, we calculated our 3 basic ratios, and basic ratio for Y was 199, basic ratio for A was 185, and the basic ratio for T is 122.5. So in this video, we're going to start with the sums of squares. So once we calculate the basic ratio, we're ready to move on to our sums of squares. And we're going to do them, I'm going to do them in a certain order, and as you're moving through the problem, you should always do the calculations in the same order that I do them. So our first sum of squares is our sum of squares A. And if you remember back from the video of when we did this the long way using the deviation scores, sum of squares A is our between subjects sum of squares. And the formula for this is actually really simple. It's the basic ratio for A minus the basic ratio for T. So moving back to these basic ratios we just calculated. It's the basic ratio for A, which is 185, minus the basic ratio for T, which is 122.5. And this equals 62.5. Now think back to when we did this the long way in the previous videos. Our sum of squares A, when we did it the long way, should be the same as our sum of squares A when we do it here the short way. And it was in fact 62.5. Next, we're going to calculate our sum of squares S over A. And again, thinking back to when we did this the long way, anytime we see this S over A, we're referring to our within subjects business. All right, so the formula for sum of squares S over A is also pretty easy. It's the basic ratio for Y minus the basic ratio for A. So it's going to be 199 minus 185. And when we do this, this equals 14. And again, I encourage you to go back and look at when we did this the long way. This number should be the same as it was when we got it the long way. And then last but not least, we are going to calculate our final sum of squares, our sum of squares T, which is the total sum of squares. And the formula for this is the basic ratio for Y minus the basic ratio for T. So we've got 199 minus 122.5. And this equals 76.5. And again, this should be the same as it was when we did this the long way. Now, a couple important checks that we want to do. We already did this the long way, but we're going to do it again here. Our sum of squares A plus our sum of squares S over A should always equal our sum of squares T. So 62.5 plus 14 should equal 76.5. It does. If it doesn't, you've done something wrong. So make sure that these numbers add up. The other thing that's important here is your sums of squares are never going to be negative numbers. The smallest sum of squares that you could ever calculate, and it would be very unusual for you to calculate this, would be a 0. So the smallest sum of squares you're going to calculate is a 0. You are never going to calculate a negative sum of squares. All right, so those are your sums of squares. The next thing that we're going to do is we're going to calculate our degrees of freedom. All right, so for every sum of squares, we have a corresponding degree of freedom. Now, if you remember back a couple weeks ago when I first introduced the idea of variance and variability, I told you that the formula for variability was going to be the sum of squares divided by degrees of freedom. All right, so the formula for variability is sum of squares divided by degrees of freedom. Now, when we did this for the last exam, we only had one sum of squares, so we only had one degree of freedom. But you can see here now I have 3 different sums of squares. So I'm going to have 3 different degrees of freedom that correspond to these sums of squares. So I'm going to show you the formulas for calculating these degrees of freedom. There's going to be one that matches up for each one of these sums of squares. So our first degree of freedom is our degrees of freedom A. And again, you're going to do them in the same order as me. So the formula for degrees of freedom A is simply little a minus 1. Now again, this goes back to the importance of doing notation right in the beginning when you're setting up the problem. Little a, if we go back to the beginning, little a refers to the number of groups or the number of levels. So in this problem, our little a is 2. So degrees of freedom A is 2 minus 1, which is 1. Next, we're going to do our degrees of freedom S over A. And the formula for this is little a times the quantity n minus 1. So our little a is 2, our little n is 5. So 2 times the quantity, 5 minus 1, is 2 times 4, which is 8. And finally, we have our degrees of freedom T. The formula for this is a times n, no parentheses, minus 1. So we've already discussed how our little a is 2, our little n is 5. So 2 times 5 minus 1 is 10 minus 1, which is 9. And before we move on, there's a check that we can do at this step as well. And the check is pretty much identical to the check that we used for the sums of squares. Our degrees of freedom A plus our degrees of freedom S over A equals our degrees of freedom T. So 1 plus 8 should equal 9, and it does. There's another way of checking the degrees of freedom T. Our degrees of freedom T should be 1 fewer than our total number of observations. And that's the case always. For every ANOVA that we do, our degrees of freedom T is going to be 1 fewer than our total number of observations. So in this case, we've got 10 observations. Our degrees of freedom T should be 1 fewer than that. It should be 9. So if we had 100 subjects, our degrees of freedom T would be 99. If we had 50 subjects, our degrees of freedom T would be 49. It's always going to be 1 fewer than the total number of observations. So that's just a good secondary check to do for degrees of freedom. In the next video, we're going to put these things together to calculate our variability.